Hello, everyone, and welcome to the TechGirl Masterclass. I am so excited to have you all here today. Now, whether you're joining from school, university, work, or you're just curious about cutting edge tech, you are absolutely in the right place. Now, today we're diving into quantum computing, a field that sounds like science fiction, but is actually becoming one of the most powerful technologies of our time. So, think unbreakable encryption, hyperfast drug discovery, and solving problems so complex even today's supercomputers can't handle them. But don't worry, no physics degree required here. We're here to simply, demystify and simplify and get you inspired, while also recognizing areas of hype, as the speakers will point out very soon. Now, before we bring on our speakers, let's quickly ground ourselves. When people hear the words quantum computing, they often think it's too complicated or too abstract or too far into the future. But our goal today is to show you that it's none of those things. So, without further ado, I will let the speakers introduce themselves, starting from the person closest to me on the screen, and that is Ellen.
Hi guys, so my name's Ellen Devereux. I work at Fujitsu as a quantum computing consultant. I've been at Fujitsu for 6 years, and my role there is to help customers figure out what quantum computing might look like for their business. I'm also a PhD candidate in quantum algorithms, so doing more of a deep dive into how can quantum computers solve problems for the real world. Hopefully I can answer some questions on that today.
Hi everyone, my name is Ray Ray. I'm a master student in physics at UCL, and I'm currently doing my research on something with quantum sensing. So in my spare time, I'm also doing a lot of community-based work for students just to inspire more and more university students to come into quantum. Yeah.
Amazing. My name is Hella. I'm a quantum and AI researcher with Exponential Science. We are a scientific foundation focusing on emerging digital technologies. A bit about my background. I'm also a master's graduate from UCL. Interesting enough, my master's was actually emerging digital technologies, so that kind of worked really well for me. The nature of my work revolves around looking at the synergy between quantum and AI and how this can be brought to industry and use case applications.
Lovely, thank you very much, everyone. Now, to kick us off, let's go back to the basics of superposition and entanglement. Now, how would you all explain quantum computing to someone with absolutely no background in physics or computer science?
I mean, I think the interesting thing, if I can go first, the interesting thing about quantum is that it literally is half computer science, half physics. So for someone with no background, it's going to have to be incredibly simplified. But I'll go ahead and make the claim that, simply put, quantum computing is simply just a new computer. The same way we have a classical system, which is the computer we have and you're probably using today, is zeros and ones. A quantum does something else, but it is fundamentally just a new kind of computer. And the more you dig into it, the more complex these concepts become. But I really hope that this session today as well doesn't act as a demotivator. If anything, just brushes up on these concepts and allows people to have more awareness about the topic and hopefully look into it a little bit more from their end.
If I can build on that, that was a great start from Hala. I think the important thing for most people looking at quantum computing and the comparison between classical computers is when you use a classical computer, you don't need to know how the transistors are turning on and off, right? You don't need to know what the bits are doing to use your computer. And long term, that's absolutely the goal for quantum computing too. You shouldn't need to worry about the bits and how they're different to use a quantum computer. But in the short term, that's where the research is how do we control those bits? How do we program those bits? And how do we know what results we're expecting to get from those bits? So that's where the real differences lie. And we haven't even touched on like how the bits and the qubits are different. Maybe I'll leave that for Ray Ray to touch on.
So I'll provide a really simple physics perspective of it. So as Wahala said, for bits it's just 0 or 1, but for qubits it can be any combination of the 0 and 1, so which means there's much more different set of combination that will give you much more different possibilities. So your processing time and power and efficiency will be much different than classical computers.
And so this is a question for the three of you again. What kind of analogy would you use to describe superposition? Do you have a favorite out there?
There's a lot of analogies, isn't there?
Yeah, I was going to say I don't love analogies in general for superposition because I feel like they oversimplify it, but that's probably not a very helpful answer.
Hala, I can see you smiling. What's
I
the
can, because there's just so many of them, and I feel like this is one I think I came up with it myself. I haven't read it anywhere. I hope it's still relevant. Please, Ellen and Ray Ray, correct me if this is completely maybe kind of outreached, but when we think of it as a painting, so when we have a classical system, you only have two colors. It's either black or white. But then when we're talking about a quantum system, imagine that you're going to do a bit of between. So you can have a gray color, and it can be a light gray or a dark gray. Now, the scientists who are very technical and they like to talk numbers would, instead of saying light gray or dark gray, would go like, oh, well, this is 30% white and 70% black. So imagine on a painting how much depth you'd have in that image just because you're able to play around with these kind of colors. I think that's the simplest way that it can be put today, other than, the famous analogy of, flipping a coin, or in regards to entanglement, spooky action at a distance.
I think that's the best analogy I've heard, and I've
Yeah.
not heard that one before. It's way better than a coin. So
There you go. You've heard it here first then.
And you mentioned entanglement then. We're not talking about the Will Smith and Jada entanglement here. We're talking about the mystical world of entanglement in quantum. What else would you use to describe that?
I mean, entanglement is just communication without like a channel for the communication, or right? So entanglement is the way that we can encode information in one qubit and share that information between qubits. Now that's very generic and it is not universal, and there is engineering that comes into how we connect those together. But in short terms, entanglement is the ability for quantum particles to share information. And they can do that without like a process. That's a really bad example. I'm not sure that we need to include that. I'm not sure if someone's got a better answer off the top of their head.
I can think of something else. Let me know if it's not the best one, because I've all the time I encounter this problem about how to explain entanglement to people. So I think the simplest way is maybe talking about a pair of gloves, which could be used for superposition as well. But a pair of gloves, you have a right hand side and a left hand side. So imagine you're doing this really simple experiment. So before you leave your house, yeah. I mean, the gloves might look similar, but imagine if they look different, and then they can't be shared between hands. So before you go out, you don't even look, you just pick a glove and put it in your bag. So, and then you go to your school, do whatever, and then before you open your bag, you have no idea which side of the glove you took. So the moment you open your bag, okay, if it's right hand side, you know immediately that the other pair that's at your house is the other side. So it's sort of like it's connected, but it's more subtle. So I think that's one of the example that you often use to try to explain this concept.
I think one thing to add that came to me whilst you were talking, and that is again a great analogy that I haven't heard before, is like it's a hard concept to get your head around. Like Einstein called it spooky action at a distance because it confused him. Now, obviously, that was because like it was a new concept at the time as well. But it is hard to get your head around and it's hard to explain. And I think that kind of summarizes how hard it is, right?
Lovely, thank you all. Now let's move on to the next section of this then, which is what makes quantum quantum. What makes it fundamentally different from what we know is more classical computing?
I guess it comes down to specifically like what is quantum mechanics. So classical computing in the classical world operates on a deterministic scale. An action has a reaction, and you know what that is, and you can expect that and calculate that. In quantum mechanics, we move to a probabilistic space, and so quantum mechanics is the physics that describes very, very small items. And so the fundamental differences of quantum computing and classical computing come from the fact that we're discussing quantum mechanics versus classical mechanics. What that means in practice is just how we encode information is entirely different.
I think to really answer this question, to put a bit of motivation behind it would make it clearer. So, why are we exploring quantum? What is the purpose of it? If classical computing is already really strong, which it is, and it's doing a lot of really difficult computations, what is the purpose of exploring quantum? And the whole idea was inspired by, I believe, Richard Feynman. I don't know how to say his name, but who famously stated that the whole world around us is based on quantum mechanics, like Ellen said. So in order to actually be able to interpret that and play and simulate it, you can't. It's unfair to use the simple, discrete 0 and 1 binary system. You would need to have a whole new system, which they've called quantum, which is able to actually depict these kinds of really difficult things that are happening all over. So that's kind of the motivation behind it, and maybe that kind of shows the difference on what classical can do and what quantum can do and classical can't.
Absolutely, that was the motivation. And I guess the concept that you can really efficiently encode data thanks to superposition and entanglement, as Ray said earlier, is further motivation to consider, well, what else can we do efficiently with quantum computers? And that direction of travel has led to a series of algorithms that have shown to have theoretical advantage over classical computation, which are very big words that just mean we can expect quantum computers to do some things better than classical computers. And that's driven the whole industry.
The some things is a very important point.
Some things double underlined.
It's not everything. Quantum is not going to replace classical 100%. But it's going to benefit a lot of things where classical is a bit weak in that point. Well, quantum can come in and maybe show that advantage. I think that's a very important point. Thank you, Ellen, for pointing it out. Only because the question, which I think Kani would have asked, but I'm glad that she didn't, is will quantum replace classical, which is always put in a panel discussion, but unfortunately, it's only some applications, not all. So it's a credit to you, Kani, and your research, if anything.
Let's go to the real world applications of quantum. What are some of the things that are really exciting you about quantum computing today? Are there any applications that you think will hit the mainstream first? And what do you think industry should be doing to prepare right now?
I think I can start from a very shallow perspective because I'm not an expert in quantum computing. I think what I see to be really applicable to the near future is maybe drug discovery, where you can stimulate and those complex molecules in a more efficient ways and find the best solution to certain diseases. And I think that's probably the best thing that we can have for a current world. And I don't know what Ellen and Hella can add on to that.
I think from a perspective of like what we're seeing drive in the markets, our customers, the ones that want to be early adopters, are definitely in the financial space. They're the ones with money to burn, and they're the ones who are expecting to see even incremental improvement, which could lead to true value. I think you're absolutely right. In terms of real world value, that will probably come in the health sciences space, although modeling complex molecules is probably a little bit of a way away, only because you need a bigger quantum computer to model a bigger molecule. So we're probably going to start with the material science space, seeing advantage first, because you're able to describe that with a smaller quantum computer, theoretically.
Yeah, I mean, if I can add on to that, Ellen and Ray took the approach of what industry it would impact. So I'm going to be looking at this a little bit differently. I do have to clarify, when talking about real-world applications, there are other things other than quantum computing. So there's quantum sensing and there's quantum communication. From what I've seen in conferences and talking to experts in the field, quantum sensing is quite mature and it's already being used for applications all over, especially in military or in navigation specifically. Quantum communication, on the other hand, attacks the whole idea of encryption schemes, and they're going to be hacked, and all your data is there. So that's kind of the umbrella under quantum communication. But nonetheless, today we're talking about quantum computing. If I had to give a definitive answer, which is kind of a combination of what Ellen and Ray said, I see it mostly in optimization-based problems. So in regards to finance, that would be portfolio optimization. In regards to what Ray said, that would be in a molecular system, and what's the combination of the best atoms or molecules that you can get to kind of optimize that problem. So I think that's kind of where we can see the most near-term application for quantum adoption.
If I can add on to that, Hala, I do agree with you. There's a lot of interest in optimization. I started my career in quantum-inspired optimization, and the only thing I'd say is that we're very good at classical optimization. So it has to be a really complex problem for quantum optimization to be required. And I'm not sure that that's necessarily the messaging in the market, because so many quantum computing companies would quite like to make sales and optimization is such an early start point. And you're absolutely right. It is like a really cool opportunity, but the opportunity for advantage is smaller, unfortunately.
That's true. Yeah, I agree with you. This is actually what we're looking to at the moment. The kind of subclass of it would be targeting the NP hard. This is a bit technical, Canny. I'm really sorry, but we're going to get
Please
into
go
it.
into the technical. We love to hear it.
Ellen, it's more towards the NP hard problems. So you have the traveling salesman problem, the max cut problems, and those are the kind of niches where there's a quantum advantage. Do you agree with that, or do you have a different opinion on that point specifically?
I mean, like, for this level, it's absolutely a valid point. On a commercial level, like when you're talking specifically like best answer, fastest answer, then quantum will absolutely be there. On a commercial level, when we're talking about industry, which is like the perspective I guess I'm bringing to this, quite often classical is good enough and probably cheaper. And unfortunately, that comes into play a lot more when you're talking about a real world application. Even though quantum would give you a better answer, it's like, but if I've got good enough, is it worth the extra investment? And like, that's not a mathematical thing. That's like the commercial thing. I don't know if that's a valid point for this audience, but it's still something to bear in mind, I guess.
If anything, I benefited from that, so thank you.
No problem at all. I'm not trying to contradict you in any way. You're absolutely right. It's just there's more factors in the real world, I guess.
That's the point of having these conversations, is really speaking to people, experts in different, within the same field, but in different kind of points of view of it, and see kind of what their interpretation of it and kind of expanding ideas on that. So if anything, that's a great point. Thank you for clarifying or for sharing that.
Please feel free to explore away, guys. We love hearing this kind of technical talk. Ray, do you have any input in this?
I think what I've heard all the time is we have to use quantum computing to solve the right problem, and not every problem needs to be solved. And I think that's exactly what Ellen was saying. And yeah, I totally agree.
I'm somewhat stealing your job, Canny, but I'd be really interested in Ray's perspective on the quantum sensing topic we touched on, because I know that that's where you're working and obviously much nearer to them.
Well, I can't say I'm an expert in sensing as well, because I'm still learning to do things. But I think that's one of the nearest possible application of quantum technology in a broader sense, because there's already like application of stuff that's used in navigation, GPS. So my project currently is more about like navigation things. So I think it looks really promising because theoretically it works. We just need to figure out how to make it more precise and how do we actually use it. So yeah, I'm really excited about this field.
So my understanding, and again, Ray's the expert here, but from a commercial perspective, quite often, for example, in military settings, you don't want to have to rely on a satellite to know where you are. And with quantum sensing, what you can do is kind of analyze how things are moving in a box that's completely isolated from the environment. So it can't be hacked, it can't be manipulated with, it can't be blocked by enemies or whatever's going on, and you're not transmitting any information. And then you're able to know where you are based on how you've moved, being tracked really, really closely by monitoring the particles in a box, basically, and by monitoring their kind of quantum, not their quantum signals, but their quantum state and how they're interacting with that box. Is a really like simple answer, but the benefit is that you're not transmitting information and you're not depending on transmitted information, and that's useful in a military setting.
I totally agree, because I obviously just realized what I'm doing is like there's no other input. The only thing we use is just an isolated environment, and we're trying to sense things basically. And then I totally agree. And then I think what it also provides a greater sensitivity, so you have a better precision of everything you want to measure. So it's pretty good for like navigation.
I've got one more cool example of quantum sensing from my research, if that's okay. that I think might be really useful for like an audience understanding of why quantum sensing is exciting. So if you've ever seen like an MRI machine or a CAT scan machine, it's a huge machine that's potentially quite scary to sit in. One quantum sensing device that I've seen developed, and I think is already in use in the real world, is like a brain scanning system that fits inside a bike helmet. And they're measuring the quantum signals coming from your brain waves, I guess. I'm not a biologist or a neuroscientist, but the concept is because of what they're measuring is much smaller, they're able to fit their sensors in a really small space. And so, for example, kids with epilepsy or kids with brain cancer, they don't have to sit still whilst they're having their brain scanned. You can get much more accurate scanning much more easily, especially for children who are notoriously bad at sitting still. And that's a quantum sensing use case that's already in use in hospitals in the UK today.
I've never heard of that before, and I'm really like enthusiastic to look into that. Yeah,
I'm going to look into that a bit more. That's really interesting.
That's a great segue for my next question then, which is kind of like predictions for the next decade. What's one way that quantum computing might change our daily lives in that sense? And I love asking this question simply because it reveals how close that feature actually is.
I don't want to disappoint you. I don't think it's going to touch daily lives in the next 10 years. I'm really sorry. Not for like the general public. I hope it touches my life because it's my career.
I will rephrase. Realistically, when do you think it will change our daily lives?
Okay, cool. I think in 10 years, we'll have the first kind of fault-tolerant, useful scale quantum computers, but they will still be small. That's our roadmap at Fujitsu, is for 2035 to have 1,000 logical qubits, which is like qubits you can actually do something with, and you can trust their answers. I know other companies are reaching milestones and have timelines to similar goals, or maybe slightly sooner, depending on the system. Some of them have gotten really good, but might not scale so well, for example. So in 10 years, I think we'll start to see those material science goals. So maybe better battery systems can be designed. But again, that won't necessarily touch everyday life, because we'll start to be able to develop better batteries in 10 years. And then you'd have to manufacture them, test them, and then roll them out. So like a customer might not see that for another 10 years, for example. Like that's the nature of research. That's the nature of R&D. I think to that extent, maybe drugs first, like small molecule drug discovery. But even then, like building a molecule that does well in vitro, in silico testing when it's on a computer, that can take 2 years, or it can take 6 months. It depends on the solution you're using. We also have a solution in that I worked on for a year and a half, so I can talk to that. But your wet labs testing and then your patient testing and like human trials, that's a really long process. So for that to touch human, like everyday life, again, you're looking at maybe 15, 20 years, because like that's how long it takes for things to filter down from research and development.
Yeah. I think to add on to what Ellen said, it's mostly going to be things behind the scenes. So it would impact industries, hospitals, organizations. But to see an impact as, drastic as, large language models today, where the average person is interacting with AI on a daily basis, I think it's still, I don't like to say the word early, but I do think a lot of the work is going to impact, like I said, things behind the scenes, things that you wouldn't really be worried about. Yeah.
Large language models, they started the research for that. Like the AI boom was in the 80s in research. My previous mentor's PhD was in LLMs, and then he had to move, well, not LLMs, AI. He had to move out of AI because there was no jobs in that space for a really long time, and now it's come back.
There wasn't even LLMs, like you said, it was AI but they were probably doing LLMs, and they were trying to talk about like natural language, but there was no name for it then,
Absolutely. So that's 45 years from theory to actual everyday life. I think quantum will come quicker than that, but not by much, and only because quantum's been being researched since the 50s.
I think what I would want to ask both Ellen and Hella, is what do you think about quantum for AI or AI for quantum? What are your thoughts on that? Because I keep hearing about this. So
I just wrote a paper about this. Just wrote a paper. It should come out on the archive in a few weeks. But and can you elaborate more on the question? So what is your incentive behind the question? Is it
I think because the two phrases different, AI for quantum and quantum for AI. So I was wondering if you can explain to the audience what's sorry Kelly for stealing your job, but like
Take over. I'm completely happy with that.
yeah, personally I'm curious about like what's like maybe you can explain to the audience what's the difference and also what do you think is a better way?
So the way I've structured it in the paper, because it can be a bit confusing, AI for quantum, quantum for AI, but you wouldn't really, if you don't really know it, you don't understand the difference. So I've actually changed the title to AI for quantum, what was it? AI for quantum hardware and quantum for AI software. Do you see what I mean? So when you're saying AI for quantum, you're looking at the quantum computer and how AI can help the quantum computer become more stable, become more strong, become less noisy. But then on the other way around, when you're doing quantum for AI, you already have an AI system, more algorithms, software side, and how can quantum work with the AI already existing, let's say, I don't know, neural network or something to make that better. So on that part, you're looking at the data and how it's being interpreted. So they are two very different paths. And the names can be a bit confusing. I've been confused by the title myself, and I was writing the paper, so you can imagine. But I think this is the best way to kind of just, when you think about it, go think of AI for quantum hardware, quantum for AI software, and then that kind of clears it up a bit, I hope.
My work was in the algorithm space, and I saw quantum machine learning to refer to quantum computing algorithms for machine learning applications, but also machine learning algorithms for quantum algorithm applications, so machine learning that would build a quantum circuit. And again, they're both calling themselves quantum machine learning, and the value in either is debatable. I'd love to get your opinion on that because it is not my forte.
On the impact of quantum and AI?
Yeah. Do you think quantum machine learning will be useful? Have you seen like genuine advantage? And do you think quantum for AI software will be useful?
I mean, I'm sure you're familiar with given that you're in quantum algorithms, you're familiar with variational quantum circuits and how they're doing and how they operate at a basic level. From the papers that I've read so far, and many papers are doing a lot of proof of concepts about how there is a quantum advantage and how this is the nearest term application to be able to actually say that you're using quantum, although it is hybrid and it is quantum and AI, but it's at least 1 foot in the door. And I think it's really funny how this coincided with the boom of AI in 2020, 2021, around then, because the architecture that was used in LLMs and large language models was it's a little bit similar to what is being used, or it needed to reach that level to be able to be used within the quantum side. And that's kind of what pushed variational quantum circuits to where we are today. But I really do believe that that is the most near-term application to be able to see quantum advantage for NISQ devices. Don't know how scalable it is, but there is an advantage. Bringing it to industry, huge amounts of data, that's a completely different conversation. But to see a quantum advantage,
that's the challenge I've seen is like, if you've got lots of data, then a quantum machine isn't going to be able to process lots of data. But that's a conversation probably for another level, unless you've got an easy comment.
That's the thing, though. I'm going to explain it to the audience for the sake of them hearing it from a person directly. A quantum circuit is it's the same basics as a classical computer. You give an input, the input's being processed, and then there's an output. Now, through this quantum circuit, we have gates. These are like the AND or of the classical system, these logic gates. There are quantum translations of that. Within these gates, we have parameters. In classical terms, we'll know them as weights. In quantum terms, we call them parameters. So the hybrid part comes in where we're getting an AI kind of box, and we're telling it, find out what are the best parameters so that we don't need to be guessing the parameters over and over again. And that significantly decreases the time taken and the processing time of a quantum computer. Scaling, you still have the same issue. Your data that's being inputted is quantum. Do you see what I mean? So that's where the scaling difficulty comes in. So the AI is simply being used to optimize these parameters. So the timing is a lot less in the sense that we're able to get the optimal kind of combination as fast as possible. But the data being inputted is still quantum, and with that comes a lot of noise as well, and then dependent on how many qubits you have, and logical or physical, and then the whole shebang of it all. I think that's simply put.
It's not an easy answer, right?
Yeah, it's not. It's really not. But it's happening. I think that's the most important thing. It's happening. It's scaling. Within every year, you're seeing more and more, whether it's hype or not, you're seeing a lot more awareness on quantum. And we were able to do a lot of, as humans, we were able to do a lot of really interesting things in the past 100 years on classical computers. 100 years ago, they probably thought, if I'm not completely mistaken, the light bulb was going to be the greatest thing in the world. And then came up with a computer, and now there's the internet and social media and everything. So we can't really see how far quantum is going to take us, but I think just have a bit of faith in humanity, and you'll be shocked at what's going to come.
If that's all on the next decade or longer, let's move on to the big one, which is Q-Day. The idea that something like a powerful quantum computer could break multiple kinds of encryption, like sensitive data, like the harvest now, decrypt later concept. Is that something that could possibly come into effect anytime soon? Is that, some people have described it as the universal pick lock for, it's a recipe for cybersecurity nightmares. How real is that risk, in your opinion? Is it all hype, or is there some truth?
No, it's absolutely real. It is a genuine risk, and I'm not pretending it's not. It is also a really long way away already. Harvest now, decrypt later is a concern, but it's a case of, is your data today at risk if it's decrypted in 20 years? Some data, probably not. Some data, definitely. And what encryption is being used to secure that data? Because, for example, Shor's algorithm, that's the most powerful quantum decryption algorithm, can break, I'm not a cryptographic specialist, so please correct me if I'm wrong, but I'm pretty sure it can break RSA encryption. But there's also AES encryption, and an awful lot of encryption, an awful lot of data is encrypted using AES, which is, it can't be broken by Shor's. It could be broken by Grover's, but the power of Grover's is less powerful than Shor's. So I'm going to break that down again, because that's a lot. And then maybe Hala can come in and summarize what I've said in a more understandable way. There are two quantum algorithms that can potentially break encryption. Shor's can break RSA. Grover's can break other types of encryption like AES. Shor's has got an exponential speed up on classical decryption methods. So it takes something that was exponentially hard to solve and makes it polynomially hard to solve. We can solve it in polynomial time. There's recently been an improvement on Shor's that is making it slightly less polynomial in time. I haven't read about that myself. Someone else told me about it recently. So there's been some improvement on Shor's, but it's still something in the region of 100 days to solve one piece of RSA encryption, roughly. And that's from a paper that Fujitsu published a couple of years ago. Grover's, alternatively, has a quadratic speedup. So it's not an exponential to polylog, it's just a square root, which is less powerful. It's going to make your decryption time less shorter, if that makes sense. So it can decrypt AES encryption, but if you increase the number of bits you use for encryption, it'll still make it far too long to be solved in a reasonable amount of time. On top of that, you've got to think about how your data is encrypted. Like if you're talking about a Skype call, that's re-encrypted every second. So if it's going to take 100 days to decrypt one piece of encryption, I'm not a crypto expert. These are not the correct words. I'm sure someone can do a better job than me. But if it can take 100 days to decrypt for 1 second, you're going to get one sound bite from that call. Whereas, obviously some data is stored in a Word file and that can be encrypted, and that's different. So it's about, what is your data? Is it data whilst it's being transmitted? is it data that's in solid storage, and how's it currently encrypted? We already have post-quantum cryptographic algorithms. That's not to say they're perfectly safe, that someone won't come along with a new quantum algorithm in the future that could decrypt those, but there are options, and it's not that big of a risk. But I'm aware I jumped in straight away there because I've got lots of opinions. Feel free to come in and have and share your own concepts and ideas.
Yeah, I mean, I have two things to say that. Ellen, I think you explained it really well, especially with Shor and Grover's algorithm. Yeah, you explained it quite well. It was very clear. There are two ways to counteract this. So that's kind of where the community is at the moment. Everyone's talking, is it going to be QKD, which is quantum key distribution, or is it going to be PQC, which is post-quantum cryptography? For the sake of making this a short call, I'm not going to share my complete answer on this because there's so much to uncover. Unbelievable amount to uncover, but it's very interesting for the audience to read about it. What I'm going to say is PQC is simply it's classical. They're not using any quantum way. They're just using classical to counteract the quantum. Seems a bit counterintuitive. They've made it work. Have a look and let me we'll see what everybody says about that maybe later. QKD is fundamentally quantum. So that counteract kind of makes sense because you're attacking quantum with quantum. So that's kind of the two approaches, and each one has obviously its own benefits, like Ellen said. So I think that's a really important point to clarify. The second thing that I do want to say is that, if anything, this is going to be a question for Ellen and Ray Ray. Isn't it important to also identify who would be able to have access to this quantum computer, that they are able to decide what they're going to do with it?
I think one thing that's really important to highlight is one of the reasons that quantum computing has had so much funding and government funding, academic funding and growth in the last 20 years is because of the threat of Shor's algorithm. I don't think that each nation would have invested quite so much in quantum computing if Shor's algorithm hadn't been discovered, because the risk is we don't want to be behind the curve. We don't want to let enemy nation, I don't like to use the word enemy, it's not a political comment, but like, we don't want to let a risky nation have access to a quantum computer because they've built one in the background and we can't even catch up. So that's, I mean, it's a net positive for the industry. But I don't think monitoring access of, say, an American device or a UK device is currently a risk. It's probably getting monitored anyway. I think the risk is other nations developing their own, other bad actors developing their own quantum computer. That's more of a concern for governments at the moment. That's based on loose interactions with public sector.
I mean, Alan, we answered the question quite well. I think it's a lot of politics talk. Governments are not going to take the risk, and if I was ruling a nation, I would probably do the same thing. And it's just a matter of time between everybody until each nation which is able to have a quantum computer has their own quantum computer and does with it whatever they decide to do with it. I hope that the quantum community will use it for good, use it for the better of the economy internally within their own nation, within their own country or organization, etc. A very, very interesting point that I would like to add is, so like Ellen mentioned, there are three kind of people, I'd say. There's academia, there's industry, and then there's government. So you see, you have these three things, and each one has their own motive. So academia is just for the sake of research. They're a bit crazy, I know. And then there's industry that's money backed, and then government which want protection. And at the moment, there are some collaborations. Some governments rely completely on the industry corporations. I dare say, for example, the States, to be able for those American-based companies. And you're making me laugh. But for their own for their own quantum systems, for example. This could be true, this could be not. I'm just giving an example because there are a lot of American quantum hardware companies producing quantum computers. Other companies, other nations, other countries are taking a different approach. They're doing it on a government base, a bit more quiet about it. And then you have institutions that are just publishing papers like crazy. They're like, everyone can read my paper. It's okay. I have nothing to hide. So it's really, from a personal point of view, I'm excited to see how these three different points are going to evolve in the future, and if there's still going to be communication between all three. Is there going to be less collaborations? Will there be more collaborations?
I think it's an ecosystem. It'll always be collaborative, mostly because, for example, government funding, at least in the UK, is limited to academic partnerships, which forces industry and academia to work together. It's quite hard to get government funding without some kind of partnership, especially as a bigger business. The UK government's done what I think is quite interesting. I don't know if this is getting a bit political, but they've specifically backed UK-only businesses, which means that they've built a really nice ecosystem of small to medium startups. I mean, like, don't quote me on this. I'm not a representative of the government in any way. But for example, the NQCC has test beds of like UK-built quantum computers, and it's supporting that as opposed to buying a quantum computer from us or IBM or whoever else is developing a quantum computer. And I think that's developed a really nice ecosystem. But like you say, every government's doing it a bit differently.
Just in the interest of time then, we're going to move on to the Q&A part of the masterclass. I've had a few questions submitted by the audience in advance. And the first one is, what kind of subjects or skills should I focus on if I want to work in quantum computing?
I mean, definitely math, physics, and computer science. That's the fundamental of everything, because it also trains you to think differently. And I think the training of the thinking is the most important part.
And what about transferable skills? I know those are very much in demand nowadays. What should they focus on there?
I mean, quantum computing companies need people who can build quantum computers and can build quantum algorithms, but they also need people to do their marketing and need people to do their sales. And a lot of when I've been involved in hiring and recruiting decisions, yes, someone with a bachelor's degree in physics but an interest in business, they might actually make a great starting point for a salesperson within quantum or a project manager within quantum, because they don't want to deep dive on the technology, and that does usually require a master's or something that specializes a little bit more. But they've got enough of an understanding of the way you think and the way you need to think to solve these problems, like Ray said, to understand the business case for quantum computing. So it doesn't necessarily mean like hardcore technologist, but if you do a bit of physics or a bit of maths, or you enjoy a bit of physics or a bit of maths, then there's definitely room for people like that in the industry.
Yeah, and there are a lot of, to add on to that, there are a lot of quantum recruitment companies that are specifically to quantum. And I saw this on LinkedIn the other day, where there was a spike in quantum project managers to be able to handle it. And that's relatively transferable skill. You can be in whatever industry. Project management will always stay project management. You're managing people and projects at the end of the day. So that is another thing to highlight on, which isn't really talked about, unfortunately. I really
think it's new. I don't think it's not that it's not necessarily talked about. I think it's just quite new to the industry at this point. Like 5 years ago, you wouldn't have seen that.
It's because it's coming to industries. Exactly. Yeah, they're starting to hire in industries. They want to use the application, so now they need a bit more higher hierarchy level to be able to kind of make that communication between both parties.
Okay, lovely. And next question from the audience is, are there any beginner-friendly tools or platforms where I can try quantum computing myself?
I mean, there's an abundance, actually. There's a lot of quantum applications in which you can either do courses and get some certificates if you want to learn, or just play around with it and see how it works. No one's sponsoring me, so I'm not going to say any names. But you can just a simple Google search on some quantum platforms. A lot of them have a lot of free services, and you can actually see it for yourself and play around with it. And that's just kind of the fastest way to really be able to see it for yourself and decide whether it's for you or not.
I can name check all of them, and then we're not upsetting anyone. How's that?
Let's try it.
There's I think there's an open source one called Quirk, which is really fun for just seeing the effect of gates on qubits. I think it's called Quirk. I haven't opened it in a really long time. Qiskit's the one everyone talks about. It's huge. It's good. It's IBM centric, and they use little endian. And one day you'll learn what little endian means, and then you'll cry because all your code's written the other way around, and that's why your code's not worked for ages. Anyway, but they are huge, and they've got a huge repository. There's PyTCat, which is really flexible between different backends. There's Classic, which is developed more from an applications perspective. So it's more for if you're an academic in other fields and want to look at applications without learning to code quantum computers. Pretty sure it's free for academics as well. So like if you're still a student, you can check that out. Qiskit and PyTCat are also open source, so free. And Quark's open source, so free. Which ones have I forgotten? There's Bracket. Don't know much about it, haven't played with it. It's probably good for some things. I think it's the only place that's got a continuous time quantum computer available to use. Which ones have I forgotten?
I think that covers it. I think that covers a good amount.
I personally did a CERN lecture series, which is probably still live somewhere. Just CERN Intro to Quantum Computing for Physicists. That's more if you're like undergrad physics and want to learn. That was great, but that's not like a platform. It's just a course.
And I think to add on to that, there's a lot of university right now, they provide quantum computing summer school, and they're targeting more like first, second year students. So definitely look out to apply to that because they're mostly free. And then I think it's a really nice boot camp to just have a week or two deep dive into these topics. And at the same time, I'm going to promote my own little organizations. So I'm working on an organization which basically teach more about quantum hardware kind of education. For example, how do you do something with superconducting qubits? And if you're based in London, feel free to check it out. It's called Quantum Engineering Design Initiative. Everything's free. We just need you to sign up to things whenever it's there. So our main motivation is just to educate more students with like different skill sets. And in the future, maybe if you're interested or if you find something beneficial from it, you can maybe work in this field in the future.
Or you can reach out to Ray and she will tell you everything.
Yes, definitely.
If you want, I can link your LinkedIn profiles to the masterclass page afterwards, and I feel like having people reach out to you and asking you more questions about the hype behind quantum and any other applications that you might recommend. Okay, I think we will end it there all. Thank you so much to our incredible speakers, Hala, Ray, and Ellen. And thanks to all of you for joining the masterclass. Now, this was our final TechGirl virtual event of the year, and we are so grateful that you chose to spend it with us. Now, if you enjoyed today's session, keep an eye out for the article I'll be publishing off the back of it, and make sure you stay up to date with next year's masterclasses and events at techgirl.hottopics.ht. Now, we're already planning our 2026 TechGirl Masterclass series, so if you have any topics you'd love us to explore, speakers you want to hear from, or ideas you're passionate about, please send them our way. And if you're not already part of the TechGirl community, this is your invitation to join us, get involved, and continue your journey with a network of inspiring women in tech. Thanks again all, and have a very good evening.